Welcome, this is the AP Physics 1 video lecture. This is on gravity. Here we're going to talk about Kepler's Law of Planetary Motion, Part 1. On the previous video lecture, I covered this slide, but I still want to review it. This connects the idea of the centripetal acceleration and the force of gravity. Notice that the gravity here is always accelerating towards Earth. There's always a pull of this object here. Okay? Force of gravity that is pulling it down. That force of gravity is this. This is what's pulling the satellite down. But it never hits Earth because it has this. So what it has here is that V, and this is perpendicular. So the V will send it to the right, but gravity pulls it down. So with gravity, it curves, right? This idea, the connection between the centripetal acceleration and the force of gravity, got us to understand Kepler's law of planetary motion. It's this idea. We see that a satellite speed does not depend on its own mass. The satellite of different masses orbiting the same distance, which is the same r, same distance is the same r here, above Earth, will have the same speed, and as a result, will have the same period. Why? V equals to 2 pi r over t. Let's review a couple of history lessons. This is not on the AP Physics 1 exam. I just want to give you a brief history lesson of where this idea comes from, in case you are on Jeopardy. The ancient idea that the sun, moon, and earth revolves around Earth is called the geocentric view. Geo stands for the earth in Greek. But in modern times, we believe in the heliocentric. Helios means sun in Greek, where the Earth is just another planet between Venus, Mars orbiting around the Sun. We started adopting this around the 15th centuries during the Renaissance in Italy. Yes, I still include Pluto as one of the planets that revolve around in our solar system. Your major figures in this is Nicholas Copernicus, who modeled the movement of the Earth and other planets in a circular orbit. His math was sort of close, but his tools were very old and ancient, right? The Danish astronomer, not quite sure how to pronounce his name, he got a bunch of data that Kepler used to develop his ideas. And to concretely, experimentally verify Kepler's laws and the data, advancements in the telescope and optics needed to be advanced. There was an Iranian mathematician, physicist, inventor. He developed the field of optics and helped the development of light and the telescope. So without his contribution, we wouldn't have the necessary tools to verify Kepler's law. So all these three major figures help contribute to Kepler's laws of planetary motion. Kepler's first law just clears up Nicholas Copernicus' idea of planets revolving around a circle. In a circle, the equation is x squared plus y squared equals r squared. Okay, x and y are points that exist on the circumference of the circle. This is the equation for any circle at the origin. But if you look at the math for an ellipse, it's completely different. They're divided by an a squared and a b squared individually. These are your focuses. Your a is at one point and b is another point. All it's trying to tell you is that at any point here, you have two distances. You have a distance here and a distance q. Okay, so P plus Q is going to be equal to something, and let's say the planet now moves to a different spot, like here. So it's going to have a new measurement to Q, to the sun, which is going to be called Q prime, and it's going to have a new measurement to the planet, which is called P prime. Did you know that P plus Q is the same distance as P prime plus Q prime? It says that the sum of these distances is going to be the same. So this is Kepler's first law. Kepler's second law is what you need to understand for the AP Physics 1 exam. So we have to take a look at the orbital velocity. So centripetal force is equal to the force of gravity. Summation of Fc is equal to Fg. Solve for the velocity. So Fg becomes that. Mp is mass of planet. Ms is mass of the sun. That is the Newton's law of gravitational field. Make the substitution. Fc becomes mass of the planet. V squared over r. This is the same thing like our satellite problem. Okay, do the algebra to solve for v squared. Take the square root. It's the same thing as before. The velocity here only depends on the radius. The mass of the sun doesn't really change. And we should solve a couple things. If the radius decreases, the tangential velocity increases. This is the reason why Mercury, which has a radius compared to Earth as 0.4, orbiting velocity around Earth would be 1.607. So Mercury's radius is smaller than us and has a larger velocity than us by 1.6. But what about if the radius increase? And we know that a planet like Saturn is almost doubled ours. Okay, so their radius is 10. And their orbiting velocity here is 0.323. Their velocity is decreasing. What you should see here is that velocity and radius has sort of a inverse relationship. Okay, I can't really say it's squared, right? Because the velocity here is squared. Yes, you can square root it. Okay. Right? So, but you need to understand this. If the radiuses decrease, the orbital velocity, if radius decreases, your tangential velocity will increase. If radius increase, your tangential velocity will decrease. Okay? There's an inverse relationship because the r is on the bottom. Let's take about the orbital period. The orbital period, the period is defined as the time take to complete one full revolution. And revolution is the path around the sun. We know that v equals to 2 pi r over t. We know we can solve for t. So multiply by t, divide by v. Make the substitution for what v was from the previous problem. And doing some algebra to clean it up, you get something like this. Okay. This equation doesn't do much for you, but you need to understand that the period here only depends on the radius. You're like, wait, what about the mass of the sun? The mass of the sun doesn't change. The gravitational constant is a constant, doesn't really change. Right? You need to understand that here the period only depends on the radius. This leads to Kepler's second law. Kepler's second law states that each planet moves so that an imaginary line drawn from the sun to the planet sweeps out equal areas in equal periods of time. So here and here. Okay. In a given period t, the planet moves from point 1 to point 2 as well as point 3 to point 4. They will sweep the same time. So like here, this is 1 month, this is 1 month. So this can be 1 month, and this can be 1 month. The planet moves more slowly on the side of the orbit right here. So here it moves slowly because it is farther away from the sun. And here it's closer, so it's going to move faster. There is a diagram to show this of Kepler's second law. Let me bring that up for you here. You should see how this planet moves slowly, then it's going to speed up as it approaches the sun. So slowly, this is just the area it's tracing out. Slowly, now watch it speed up. See, it's speeding up, speeding up, speeding up. That's why it traces that faster. So all this area that it traces out is equal to each other. Okay? Slow, 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 slow. Slow. Pick up speed, pick up speed, pick up speed, pick up speed. Faster, 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 faster. Start slowing down, start slowing down, start slowing down. Yep. All right. Now we can take a look at the vectors to see that. We saw that the vectors here increased. Okay, so we can say here, this is long, so this is V. And we saw that it got larger, so I'm increasing the length of the vector. And right here, this is when it's the V max. This is the fastest that it's going to be. Then it's going to start slow. Right? It's going to start slowing down. So I'm going to start decreasing the strength of the vector here. All right, this should be smaller. And then right here, this is when it's V minimum because it's the farthest away. Then here it's gonna pick back up. All right. So from here to here, the tangential velocity is going to increase. Then from V max to V min, from here to here, the tangential velocity will decrease. Okay. Now we want to look at the centripetal force, or the force of gravity. So we saw that if the object's here, look at the radius, right? The radius here is the smallest. So here, this is when it's going to have the largest FG. Okay, because look at the radius. Then from here, it's going to be slightly smaller, right? Then here it's going to be slightly smaller. As it keeps going, notice how the distance decrease. Right? Okay, here it's going to be super small. Okay. The reason why it's super small here is the force of gravity isn't pulling as much. Okay. And as it comes closer, it's going to start increasing more, and it's going to start increasing more. All right. Here, what you should see is that there is a direct relation. There's an inverse relationship from the distance. So the farther away it is, it has less gravity pulling on it. Okay. So this is what's happening. So as the object is coming closer to the sun, it starts speeding up, right? Because in theory, notice how the force of gravity is pulling it in towards the sun. So it's going to keep coming, and it's going to try to get pulled into the sun. But as it approaches, velocity increases. Velocity is going to increase to the point that at this point it's going to hit its V max. Then, because you see how velocity is increasing, that's what allows it to swing across the sun and never hits the sun. Then it swings around and it comes on this side, the V starts decreasing. So V starts decreasing and FG is going to start pulling it back in. Okay, then it repeats. Okay, velocity's more, it's going to go faster. FG's pulling it in, FG's pulling it in, FG's pulling it in. Then it's almost going to hit the sun, but V increases, so it keeps swinging around. Lastly, I want to show you a quick video of the planetary, the satellite's orbital mechanics of Keplers Law. This is an old video, but very educational. There you go. That is everything that you need to know in terms of Kepler's law of planetary motion.